Hello, geometry students. This is Miss Graham, and today we are going to be looking at lesson 19.2, the geometric mean. So go ahead and pull out pages 278 through 280 in your textbook. We're going to go ahead and start off with our learning targets up at the top. So our first one for today is that we are going to identify the relationships that exist when an altitude is drawn to the hypotenuse of a right triangle. And we're going to apply the relationships that exist when an altitude is drawn to the hypotenuse of a right triangle. Remember from our previous lessons that when we have a right triangle, we can draw an altitude and create two more right triangles where they all have a similar relationship with each of their side lengths, so that there is some scale factor that we can multiply to get from one to the other if it gets bigger or smaller. And remember, an altitude is drawn from the right angle of our big triangle all the way to the hypotenuse, and it creates another 90-degree relationship, which makes our two smaller triangles right triangles. So let's go ahead and look at numbers 1 and 2 to start off with right here. So number 1 says, which two similar triangles allow us to show that x over t is equal to t over z? So remember, building off of our last lesson, we were able to look at and we can compare, maybe a leg and a hypotenuse or a leg and a leg within one triangle, such as in a fraction form, and set it to another fraction form. Or we can compare the same triangle within each other, looking at the numerators versus the denominators. So either way works. Let's go ahead and start off looking at the fraction form. So comparing our top and bottom in our fraction. So looking at all of our triangles, I'm looking to see which have a side of x length and a side of t length. So I can see that it's within this smaller triangle right here. So I'm going to go ahead and highlight that red. So we know that we are looking at the relationship between two sides in that smaller triangle. So we can see that x is really going to represent the smaller leg or our shorter leg, and t is going to represent the long leg length. So, hold on, let's try spelling leg again. There we go. So now we want to just verify, okay, what's the other triangle that we're looking at, where we're looking at t is the short leg and z is the long leg. So we have two triangles left that we're going to be looking at. Okay, so I see a length of t, again, is going to be this measurement. And then I have a length of z, which is going to be this measurement. So I know I'm going to have kind of that medium triangle that I'm going to be comparing, where I have the short leg on top, the long leg on the bottom. So now we want to figure out how we can write the two triangles that are similar. So remember, we want to have a triangle is similar to another triangle. And we want to make sure we're calling them by the vertices of each of the corners. And we also want to make sure we follow in the same order. So let's say I'm looking at my red triangle. Let's say I start off naming it A, E, S. So let's start off naming that triangle let's try again. A, E, S. And I want to make sure I match the exact same letter order, right? So I'm kind of labeling the hypotenuse, then the short leg, and then it comes back to the long leg. So looking at our blue triangle, the best place would probably be to start here to label the hypotenuse, YA, and then come back for the short leg for S. So I'm going to go ahead and label that similar triangle YAS. So yes, there we go. So we got our two similar triangles matched up. Now let's look at number 2. So which two similar triangles allow us to show that x over u is equal to u over p? So again, I want you to go ahead and look at this relationship. We can look at it again, comparing the top to our bottom, or we can compare it from our numerators to our denominators. Let's try looking at this and comparing our numerators and denominators. So this time we're going to look at side length of x and u. So which triangle has a side length of x and u? Again, that's going to be our red triangle. So we have x and u. We have the short leg and the hypotenuse. So I'm going to go ahead and kind of color coordinate across like this. So we know that now we're going to be comparing here the short leg, and here we're going to be comparing the hypotenuse. So we know below this is going to be the short leg, and that's going to be the hypotenuse for one of the other triangles. So go ahead, see which other triangle has a short leg of U and hypotenuse of P. As we can see, it's actually going to be kind of our big triangle here, the one we haven't looked at yet. So I'm going to go ahead and kind of shade that in yellow. So looking down here, we can see that's going to be the big triangle. All right, now I want you to try to list the two similar triangles, but I'm going to help you out with the first one. So we know the first one is going to be triangle AS. So I just chose that letter order. Again, you can choose any letter order for the first triangle. I figured let's keep it the same as our last triangle, but I want you to go ahead, pause the video, fill in which triangle is that congruent to. All right, since YES, again, lists the hypotenuse first. In our big triangle, we should list our hypotenuse first. So that's going to be YE, and then we go down to our shorter leg to. So that way now we have YEA. Nice. Good job if you were able to come up with that. Let's keep on exploring below. So let's go down right to here where it says the answers to items 1 and 2. So what we just answered right on up here, they indicate two corollaries of a right triangle altitude theorem. So remember, our theorems are set rules that we already know exist, and corollaries are kind of like subsets of rules that break off of the big ideas, those big theorems. So we're going to go ahead and look at two of these. So let's take a look at corollary number 1 first. So it says for corollary number 1, when the altitude is drawn to the hypotenuse of a right triangle. So going back up here, we're saying when our altitude is drawn to the hypotenuse of a right triangle, got it. We know the length of the altitude is the geometric mean. So that's a new vocab word for us. So the length of this altitude, what we're calling T, is going to be the geometric mean between the segments of the hypotenuse. Now, we're not really sure what geometric mean means again, but what we're going to do is we're first going to start off looking at this first corollary and bring it to number 3. So that's going to help us understand what geometric mean is. So in item number 2, so problem number 2, right? We use properties of similar triangles to justify this statement, right? This proportion right here. X over U is equal to U over P. Now it wants us to solve the proportion for U. So we're going to want to isolate U, get it by itself. So in order to do this, we're going to actually have to do some cross multiplying. So remember that from one of our previous lessons. So we're going to cross multiply and set the products equal to each other. So I'm going to have U times U equal to X times P. Now instead of writing U times U, we can say U squared, right? Going back to properties of algebra. So U squared equals XP. Okay, how do I get U by itself? Well, I got to take the square root. Remember, that's going to be the inverse operation of squaring. So that way I have U by itself. And that is going to be equal to the square root of X times P. So what this tells us is our geometric mean. So I'm going to write that down here. So our geometric mean right here, right there, is going to say that whenever we want to find a certain length, right? Whenever we want to find a certain length, we can actually use these rules to kind of help set us up with what's happening. In order to find the length of U right here, what we can do is we can take this length of X times this whole length of P, multiply them together and get the square root of it. That will always be the length of U. That's what our geometric mean is. And that will always work whenever we have a right triangle with our altitude drawn. Because again, it goes under the right triangle altitude theorem. So that's our kind of first corollary, our first rule that we're noticing what happens. This will always, this will always be true. Now, something else that we're going to notice as I zoom out a little bit is that we are going to look at corollary number 2. So corollary number 2 says when the altitude is drawn to the hypotenuse of a right triangle, just like what we have above, we're going to learn each leg is the geometric mean between the hypotenuse and the part of the hypotenuse that is adjacent to the leg. Now, this is kind of a little bit hard to understand. Don't worry, we're going to go back to it and talk a little bit more about this corollary, but I'm going to focus a little bit more on geometric mean so you can have a little bit of a better understanding of this. In order to help us out with this, we're going to go ahead and start to look at the next page, and we're going to look in the margin where it says geometric mean and talk about that example. So we are on the next page. We are going to zoom in to geometric mean right here, and we're going to try to talk about it a little bit more. So the geometric mean of two positive numbers, a and b, is the positive number x such that, remember, when we had our proportion like this, we saw previously that one of the diagonals, right before it was u times u, one of the diagonals is going to be the same value. In this case, it's going to be x. The other one is going to be two different numbers. So before we had x and p, and then we had u's across the board. So when we solved it, we had u equals the square root of x times p. That's going to be the same thing here. We're going to have x is going to equal a and b multiplied, and then we take the square root of that. So that's what we're looking at. When we solve, x will equal the square root of a times b. So what we're going to learn looking at this with examples of numbers is that 6 is going to be the geometric mean of 4 and 9. Because let's say we set up this proportion where we have a and b are 4 and 9, and we're not sure what x is. Think about this. When I cross multiply, I get x squared equals 36, right? So then wait a minute. When I take the square root of 36, which is 4 times 9, I end up with 6. So that's how we're tying this idea of geometric mean all together with our triangles. Essentially, what we're going to be doing is we're going to be trying to solve for different pieces of our triangle when we only have a certain amount of information. And I can tell you, it's not going to be always using Pythagorean theorem for every single aspect. We might not have enough information to use the Pythagorean theorem. So this is another way that we're going to encounter this. So let's go ahead and we're going to start to look at example A to understand this a little bit better. So example A up here says, given triangle DEF, so we have DEF, beautiful, with our altitude FG, we want to determine what x is. So we want to determine what the altitude is. And we also know what y and z are. So we know what y and z is. So my first piece would probably be to list out what y is. Y is 9 and z is 36. So looking through these steps, we're going to use the corollaries that we looked at before to determine the relationship. Because obviously you can see we have one piece of information from each of these triangles, and it's going to be impossible to use the Pythagorean theorem to solve from there. So we know we have to use the geometric mean and what we learned on the previous page. So it says the altitude is drawn to the hypotenuse of a right triangle, as we can see. So the altitude x is the geometric mean between the segments of the hypotenuse y and z. So what we're going to do here is we're going to look at seeing, okay, how can we go about this? How can we use this information of part of our hypotenuse kind of divided into two pieces and our altitude to figure out how to solve for the altitude? Well, what we're going to notice here is that we are going to make sure we're using our geometric mean. Now, before we were able to come up with some type of equation looking at how we compare the different triangle legs and hypotenuses to each other. So that's what we're looking at here. We're going to put x as the diagonals. We know it's one of our diagonals. It doesn't matter which one. So I put x across from the x. And then we have kind of our hypotenuse, right? We have our hypotenuse divided into two lengths. So that's where I'm going to put y and z, or essentially 9 and 36. It doesn't matter which one you put where, as long as, you have them across at your diagonals. We're going to end up multiplying them again So I'll get 9 times 36, and I'll get x times x to equal x squared. So that way I have x squared equals, well, 9 times 36. So I'm going to see I get 324. So essentially what we're doing is before we came up with relationships of similar triangles before. Now we're using this pattern, calling it the geometric mean, to help us find what our altitude is if we do know parts of the hypotenuse of our big triangle. So following suit, we take the square root. We end up getting 18 as our length. So in order to find the altitude, we have to know these two pieces of our whole hypotenuse of the big right triangle. Now, let's say I wanted to find out maybe what y was, and I was given x and z. We can actually also do that as well. Or let's say I wanted to find z, and I knew x and y, kind of these lengths, I'd be able to do that as well. So really, the big piece that we're looking at here is looking at the altitude, right, is drawn to the hypotenuse of our right triangle. So the altitude x will be the geometric mean between the segments of the hypotenuse, y and z. Again, I know this is a little bit confusing. This is one way that we are going to approach looking at how to solve for our altitude, or how to solve for one of the segments of the hypotenuse if we're given the other pieces of information. So I'm going to have us go ahead and complete the try these A below. So we're still actually using this figure above, but now we're not going to have 9 and 36. Now, we're going to have some different values, maybe for y, z, and x. So let's go ahead and look at A below. I'm going to help you out with this one, part A under Try These A, and then I will have you look at part B on your own down here. So sometimes it's helpful to redraw the picture, so that's what I'm going to go ahead and do. Just make a nice sketch of my picture. Oh, let's try that again. Make a nice sketch of my picture. Off to the side where I have D, E, and F listed. And then remember, this is our big right triangle. I have my altitude drawn, so that way I have two smaller right triangles. So this is point G. And then I'm going to have Y listed as the length there, Z, and X. So looking at our problem, it says if Y equals 2, and if X equals 16, let's try that again. I want to find out what Z is. So let's start off by, we could write this formula if we wanted to start from that point. But what's really nice is that we can use this idea up here. We can start off filling in some information right there. Now it's going to be a little bit different, right? Essentially from here, we're saying that we're taking the square root of y times z equals x. So that's essentially what we're going to be filling in here. That's that formula. So we have x equals the square root of y times z. But looking at this, we're not really solving for x. We know what x is. So it actually might be easier to use this formula instead. Either one really works, but for us, since we're finding out what z is, it might be better to start off with something where it's, we already are undoing the square rooting. So I'm going to start off with this part of the formula. So we have x squared equals y times z. Let's fill in what we have. So we know what x is. That's 16. So we're going to do 16 squared equals y, which is 2 times z. So now it's a little bit easier to solve for z here. We're going to do 16 squared, that's 256 equals 2z. And then I can divide both sides of my equation by 2, so that way I get 128 is equal to z. So having the picture here really helps out with that, and understanding how our given formula can be rewritten two ways and seeing which way is the best to use. So I'm going to go ahead and have you pause the video right here, and I want you to go ahead and try part B on your own, where now we're given x and z and you have to solve for y. Alrighty, I was able to redraw my picture. I put in what z and x were, and I decided to use the formula of x squared equals y times z, again, because we weren't solving for x this time, we were solving for y, so that formula seemed easier. I ended up getting 7.2 as the length of y. So now, again, that we've been able to practice some of these examples, let's go ahead and just review how, again, we can explain the use of this corollary to find a certain length. So go ahead and turn to our next and last page. So let's go ahead and zoom into number 5. So number 5 says, explain how to use the corollary on the first page of this lesson to find JM. So I'm asking you in words how we can find the altitude. So I want you to first explain it, and then we will find out what it is after. So go ahead, pause the video right here. I want you to try explaining it for yourself, and then we're going to come back and compare answers. All right, so here's what I responded to as my answer. I know we're looking at corollary 1, so that's the altitude of JM is the geometric mean of KJ and JL. So this is geometric mean of KJ and JL. So this means we can find out what x is by taking the square root of 12 times 48. So that's exactly what we're going to do. We can go ahead and do that in the margin. So we know to find JM, the length of that, we take the square root of 12 times 48. So when we do that, we have 12 times 48. That is going to be, we end up getting 576. And then when we take the square root of that, we should end up getting 24. So we know that the length of JM is going to be 24 units. Now's the time of the lesson where you're going to refer back to your teacher and see what your homework is for tonight. For Miss Graham's class, watching this video and taking notes over it is the only homework. So I will be seeing you in class tomorrow. Have a good day.